Okay, I suppose we can start. So, I welcome you all to this live interaction and problem solving session for the subject engineering mechanics. So, today we will be dealing with problems from the contents of week 9, that is to do with accelerations, relative motion acceleration, parts of rotation, and rotating frames of reference in parts. So before I begin, I'd like to emphasize you please solve the questions along with me. Should you get stuck somewhere, or if I make a mistake, you can readily point it out so that it is beneficial for you ultimately. And in case you have not, there is a forum in Swayam portal. You can join that and ask your questions there also. So with that, yeah. So other than that, people who are joining midway are more than welcome to join. So with this, let me start and go to the first problem of the day. The absolute distance of the instantaneous center of zero velocity in meters from the gear center is what is asked. So we have been given a rack and pinion arrangement where we are told that the top rack is moving right with a velocity of 1.5 meters per second, and the bottom rack is moving left with a velocity of 0.25 meters per second. And we have been given a gear whose mean radius is 2.5 meters. That's what is given. So essentially, the idea is there is no loss of contact between the rack and the pinion. There is no relative slip. In which case, the point on the pinion also will have the same velocity. Is the idea here. So if we were to take this and see that the velocity of this point is 1.5 meters per second, and the velocity of the bottom point is 0.25 meters per second. So if you were to connect it by a straight line, so the way to find the instantaneous velocity is join the ends and join the tip of any two velocity vectors that is known in a rigid body. You join the tips and join the heads, and wherever they intersect, if they intersect, will be the instantaneous center of zero velocity. So the entire setup can be assumed to be rotating about that point momentarily. So, okay. So this is 0.25. This is 1.5. And do we know this distance? This is nothing but twice the radius, which is 5 meters. So if we take this to be x, say, then this will be 5 minus x. This distance will be 5 minus x. So rest is straightforward, 0.25, and we have 1.5. So by similar triangles, we can write 0.25 by x is 1.5 by 5 minus x. So what will this come out to be? It will be 5 by 4 minus 0.25x will be 1.5x, or x is nothing but 5 by 4 upon 0.75. Yeah, into 4 by 3. I'm doing it correctly. 7 by 4. Sorry, 4 by 7. Sorry about that. So I'll just take it. It is 1.75. Yeah, inverse into 5 by 4. So our x comes out to be 0.714 meters. But we have to keep note that x we have taken from the bottom. So what has been asked is from the gear center. So it is nothing but our radius minus this value. So the distance of ICR, or instantaneous center of zero velocity, or however it is called, is nothing but 2.5 minus 0.714, which comes out to be 1.785 meters. So once this is known, what is the implication of knowing this? If both the velocities were equal, then the ICR will coincide with the center of the gear of the pinion. So at this moment, given this velocity, we are able to see that this is not at the center, but it is at a distance of 1.785 meters. from the center. So at this moment, we can assume the entire thing to be, we can consider the entire setup to be rotating about this point and thereby find velocities and accelerations of other points. So are there any questions based on this, or shall we move on to the next problem? If there are any, I'm happy to take them now. Okay, so I take it that this is clear. So I'll move on to the next problem. This has something to do with the Coriolis acceleration, which is something that has to be accounted for when we deal with rotating frames of reference. So, okay, let us look at the question. So answer the following questions based on the data given therein. Which of the marked numbered vectors correctly depicts the Coriolis acceleration vector? So there is a body which is having a relative acceleration with respect to a rotating frame, which is this arm, so to speak, and that slider is having a relative motion with respect to that, and the direction of that relative motion is given here, pointing downwards, and the rotation of this arm itself is given to be in the uh, one thing we need to be careful here, not maybe for this problem, but we should correctly identify that this is x and this is y. So x cross y here is out of the plane of the paper. There might be cases where x might be pointing that way and y might be pointing the same. So in which case we will be using the right hand to identify which is the plus z direction. That is something we just need to keep in mind. Anyway, so we have this thing pointing out of the plane of the paper. So that is omega. So we know what is Coriolis acceleration. A Coriolis is given by 2 omega cross VREL. Okay, so this is the relative velocity relative to the rotating frame of reference, and this is the omega of the rotating frame of reference. So we will be able to see that this is outward, this is pointing out of the plane of the paper, and if we were to cross with this VREL, we will see that this is uh, out of the plane of the paper is this direction. Let me just draw it a little neatly. So I have that crossed with something that is going like this, parallel to VREL. So our actual Coriolis acceleration vector points in direction 1. So this is our correct direction. Okay. So the second part says, what is the magnitude of this Coriolis acceleration in meters per second if omega is 2 and VREL is 0.75? It is just a simple substitution. The idea behind these questions is to just familiarize yourself with small bits and pieces of the bigger picture and together assemble them in a different problem. So A Coriolis is nothing but 2 omega cross VREL, as we have already seen. So magnitude of A Coriolis is 2 omega VREL. So this is nothing but 4 into 0.75. So this is 3 meters per second squared, pointing in this direction. So in order to account for its acceleration from the fixed frame, we need to add one Coriolis acceleration component as a correction to this, because this relative velocity is with respect to the rotating frame. So this is something to be kept in mind. So, okay. So, yeah, yes, yes, yeah. Okay, so if you were to resolve this into two components, this is constant, this is constant, this is what is changing. So that change only is represented as VREL, if you see. See, no, that's fine. That's a good question. See, I will just repeat the question for those who have not perhaps maybe understood. Uh, the thing is, if we take absolute motion equations, and derive that circular motion, we automatically get omega dot 2 omega dot theta dot is what we get as a Coriolis component which comes through mathematics itself. We just need E theta. Yeah, yeah, yes, yes, of course. So I was just talking about this thing, the magnitude. So essentially, if we were to consider this to be rotating about this point, if this is the vector r, then the why shouldn't we consider r dot here? Essentially, we are considering r dot only if we were to decompose this into two vectors. This change, see this uh, this pink vector, which is a component of R, is constant because the arm is at a fixed distance. So essentially, our yellow component is what is changing. So if you see that yellow component is parallel to VREL, so VREL is essentially that vectors the change of time rate of change is what is VREL. If we see R is reducing because VREL is pointing downward, that object slider is moving down. So essentially, howsoever we take it, it will come out to be the same. Okay, so are there any other questions? Okay, so if not, we will move on to the next problem. Hi all. So the question which was solved in the live session that had a little bit of a numerical error, so I thought that I'll re-record this session alone for the solution for this question alone, so that when you refer back to it, you have the correct solution with you. Okay, so let us just read the question quickly. A slotted link is connected using a pin on a disk that rolls without slipping as shown. So this pin is connected to this disk and this disk is rolling without slipping. At the instant depicted, the angular velocity and angular acceleration of the disk is 1.75 and 1.5 respectively in the direction shown. So we have been given the direction. So based on the given data, answer the following questions is what has been said. Okay, so from this we can see that omega disk we can write as minus 1.75 k cap because it is pointing into the plane of the paper, the axis, and alpha of the disk is nothing but 1.5 k cap. Okay, and also we have been told that the disk is rolling without slipping. So let us name this point O. Let us name this point of contact C at this instant. So we know that our instantaneous center of rotation or instantaneous center of zero velocity is point C. Okay, so we have been asked some questions. One is, if Vp with respect to r denotes the velocity of the pin P as perceived by an observer rotating with the slotted link, then the x and y components of that are, and then magnitude of the angular velocity of the slotted link and total acceleration of pin P is what is asked. So here we can see that C is the ICR. So we know that our velocity of P will be perpendicular to this point. So this is our velocity of P vector. Okay, velocity of P vector. Now what is asked is, if a person were to be rotating with this slotted link PS, RS, then what would the person observe as the velocity of P? So we know that that will be along the slot is what the person will observe. So the third component to this, we can simply complete the triangle and we can write that as the normal velocity. So let me draw it separately. So if this is my Vp, velocity of P as perceived by that observer will be Vp with respect to r, which is parallel to the slot, and there is another velocity, let us call this V normal, which is normal to the slot at point P. So using coincident points, we saw that we are able to get the directions. Now what is left is getting the magnitudes. So first, absolute velocity of P we are supposed to compute based on the constraints given. The constraints being that it is rolling without slipping and the dimensions are given. So let us go ahead and do that. I have drawn this for convenience. Let us do it now. Okay, so from triangle POC, we can see using cosine rule that TC squared is nothing but 1.1 squared plus squared minus 2 into 1.1 into 1.5 cos 118 degrees. So PC comes out to be 1.5 into cos 118. 5, so root 5 comes out to 2.24 meters. So our PC is 2.24 meters as was there. All right. Now velocity of P, absolute velocity of P we can write as absolute velocity of C plus omega disk cross R P with respect to C. Now we know since this is the ICR, this is 0. So from here we can write magnitude of Vp is nothing but our magnitude of this thing, which is magnitude of 1.75 into RPC. Magnitude is nothing but the length of that vector, and length of that vector only we found out PC to be 2.24. So this is 2.24. Therefore magnitude of velocity of P comes out as 3.92 meters per second. Okay, so now that we know this, using this velocity triangle, we can solve for the unknown velocities. So let us call this angle as some delta. So we can see that Vp with respect to R is nothing, magnitude is nothing but Vp magnitude cos delta, and V normal is nothing but Vp sin delta. Okay, now it begs the question, what is delta? Let us complete the triangle here. I'll just use some other color maybe. So this is point P. This is 1.1. This is 1.5. This we know is 2.24. 1.1 meter. This is point O. 1.5 meter. This is point C, point P. And we have our velocity like that. And then its component is like that. So this we know to be delta. Okay. Now, if we were to use the sine rule on OPC, triangle OPC, then this angle we know is 118 degrees. So 2.24 by sine 118 is nothing but our angle, our 1.1 by sine angle OCP, which is nothing but 1.5 by sine of angle OPC. So from here angle OCP comes out to be 1.1 by 0.24, 25.69 degrees, and angle OPC comes out to be, we can simply add 118 and subtract it by 180. So we will get this as 36.30 degrees. So this angle is 36. Okay, this is 25.69. So naturally this will be 90 minus 25.69. that makes this angle 90 minus 25.69. 90 minus 25.69. Okay, so from here we can write, let me call this some other angle, maybe beta. Okay, so beta plus 90 minus 25.69 is nothing but 90. So beta comes out to be 25.69 degrees. And we know that this, the line that is along the slot, from the question it is at an inclination of 75 degrees. This is 75 degrees given in the question itself. So we can see that our delta plus beta is 75 degrees. So delta we can calculate it as 75 minus 25.69, which comes to 49.31 degrees. So rest is straightforward. We know this. We have determined delta. So what is our Vp with respect to our magnitude? Is nothing but Vp magnitude, which was 3.92 cos of 49.31, which comes to 31, 2.55 meters per second. Likewise, V normal is nothing but 3.92 sine 49.31, which comes to sine 49.31 comes to 2.97 meters per second. Okay, so we know that the magnitude of this velocity v p with respect to r is 2.55, but they have asked in component form, so we just need to resolve it along the x and y axis. So we know that VPR is along the slot, which is at an inclination of 75 degrees with respect to the horizontal. So this is VPR, and we know that this is 75 degrees. So if we were to write this in vector form in the xy coordinate system as shown, it will be nothing but 2.55 cos 75i plus 2.55 sine 75j. So P with respect to R is 2.55 cos 75 is nothing but 0.66 I cap. 2.55 into sine 75 is plus 2.46 j cap. Okay, so we have finally arrived at the velocity. Zero point 0.66 and 2.46, these are our answers. So this is 0.66 and this is 2.46 meters per second in component form. Next is asked magnitude of angular velocity of the slotted link is what is asked. So we know that magnitude of velocity of the slotted link, angular velocity of the slotted link, let me call this a omega SL into r of p with respect to r is my normal vector, its magnitude from the geometry. So omega slotted link magnitude into r of p with respect to r is nothing but the distance. Magnitude of that is this distance, which is given as 2.75 meters. So this into 2.75 gives me V normal, which we calculated here as 2.97. So we can see that omega of the slotted link magnitude is nothing but 2.97 by 2.75 comes to 1.08 radians per second. And from the geometry, we can see that it rotates in the anti-clockwise direction. Okay, next. So this also we have got. Next, we have to calculate the magnitude of acceleration of p. Okay, so this we have invariably we have to do this by vector analysis only. So let us do that. So velocity of p, sorry, acceleration of p, we can write it in many ways with respect to many points. Let us write it with respect to point C, which is the ICR of this problem at this instant. So acceleration of C plus omega disk cross R of P with respect to C plus alpha is cross R of P with respect to C. So acceleration of C here, we know it is pointing towards the center. The magnitude we can easily calculate as omega disk squared into R radius of the disk, which comes out to be 1.75 squared into 1.5. So acceleration of C is 4.59 meters per second squared J cap. So and then R P with respect to C, the magnitude we know this to be 2.24 meters. If we were to resolve this into a vector form, so it will come out as 1.1 minus 1.1 cos 28 I cap plus 1.5 plus 1.1 sin 28 j cap. This can be seen from the geometry. So Rp with respect to C is nothing but minus 0.97 I cap plus 2.016 j cap. So this also we have got. So the last thing is to substitute and get the acceleration of P, which comes out to be 4.59 j cap plus minus 1.75 k cross minus 1.75 k cross minus 0.97 I plus 2.016 j plus 1.5 k alpha 0.97 I plus 2.016 j. So this we can simply resolve. I suppose this is where there was some arithmetic problem in the addition and the answers didn't come out quite correctly. So let us do that carefully now. So it was minus 1.75 squared into minus 0.97, the I component from here, and then we will have minus 1.5 into 2.016. This is my I component. J component is 4.59 is already there, minus 1.75 squared into, put the squared outside, into 2.016 minus or rather plus 1.5 into minus 0.97 j cap. So acceleration of p, if we were to simplify this, will come out to be 0.97 minus 1.5 into 2.016. It is minus 0.05 I cap 4.59 minus 1.75 square into minus 3.039 j cap. So this is what it comes to. So our magnitude of acceleration of p is what is asked. So we can simply calculate this. This comes to 3.04 meters per second squared. So this is our final acceleration of p, 3.04. Let me put that in red itself. So it is 3.04 meters per second squared, and the angular velocity we had got as 1.08 radians per second. So it is essentially the same as we had solved in the live session, except that there was some arithmetic problem. Some calculation plus or minus got interchanged, which is why we were getting some other answer near about 2.63 or something, I think. But the correct acceleration of point P is 3.04. So I request all of you to please take note of this. And the same corrected solution is what is posted in the Google Sheets also that is shared with this video. So thanks. So let us move on to this problem. A cannon barrel which is being raised by a wedge fires a cannonball. So this wedge is being pushed towards the cannon, and that is how it is being raised. And it fires a cannonball which is at the end of the barrel. At this instant, it is at the end of the barrel, which is of length 6 meters. Okay, and moving in a direction shown with constant velocity. Okay, so our velocity is constant. Further, the cannonball has, okay, this is constant, I'm sorry. Further, the cannonball has a velocity and acceleration of 25 meters per second and 5 meters per second square, both measured relative to the barrel. So essentially, our VREL is given to be, the magnitude of VREL is given to be 25 meters per second, and our magnitude of AREL is given to be 5 meters per second squared. So we are, if we were to take that, in the lecture, if you would have seen, it is a convention to write it in small case, the rotating frame of reference. Both measured relative. So this is given. So far, so good. And this we have been given, it is constant. Okay. So ignoring the effect of gravity in this scenario, answer the following questions. So what are the questions? Which of the following expressions correctly represents the angular velocity of the cannon barrel? So from the very look itself, we can note that it is a small part of absolute motion. So if we were to take this triangle, that triangle, so we can see that tan theta is 2.2 upon, let me call this d. So it is 2.2 upon d. So d tan is 2.2. If we were to take d dot tan theta plus our d theta dot secant square theta is 0. So theta dot, what does it come out to be here? Minus d dot tan theta upon d secant square theta. So, okay, we have been given this in terms of other quantities. So let us simplify further. I'll just simplify it here. Yeah. D dot tan theta upon d is our 2.2 by tan theta. 2.2 by tan theta. So it is tan square theta secant square theta, which comes out to sin square theta minus d dot upon 2.2 tan square theta upon secant square theta. Yeah. Sorry. Yes, I mentally did the opposite. I multiplied by cos square theta. Okay. So d dot, what is d dot? Is nothing but our v. So this is nothing but our minus v sin square theta upon 2.2. So we have this. All right. So let me just move it here. There is some space. Okay. So we know that theta dot now is minus v sin square theta upon 2.2. So angular acceleration is asked. So similarly, we have to do the same. Theta dot is minus v sin square theta. So 2.2 theta double dot. We may as well have divided it by 2.2. Okay. So minus v dot sin square theta minus uh, v sin 2 theta to theta dot. Okay. So this is 2.2. I will remove it from here. V dot. It is given that it is a constant velocity. So this is 0. This is 0. So what is our theta dot? It is essentially minus v theta dot sine 2 theta by 2.2. So we would have to be given what is theta. Yeah, it is given. So it is at 48 degrees. At that instant, theta is 48 degrees. So let us calculate theta dot at that instant. Theta dot, we just got it as minus v sine square theta by 2.2. So mind you, v is negative. So it is minus 2.2 sine squared 48 by 2.2. I think that is 3, right? 2.3. Yes. So what is our theta dot? Sine 48 squared into 2.3 by 2.2. It is 0.577 radians per second. Okay. So theta double dot, we can just substitute minus 2.3 by 2.2, 0.577 into sine of 48 into 2. So what do we get this as? It is positive. So 2.33 sine 48 upon 2.2. So it is 0.6 radians per second squared. Angular acceleration magnitude is as, so this is 0.6 radians per second squared. So we have got omega, we have got alpha. All right. So let us write that for this cannon barrel, omega is nothing but our theta dot, which is 0.6 k cap, and alpha is, sorry, this is 0.577 k cap. I beg your pardon. 0.577 k cap. Alpha is 0.6 k cap. Okay, so far so good. So where we are connecting the rotating frame of reference to the cannon barrel, so we have the RFR of uh, that quantity. RFR, the angular quantities of the RFR. Okay. Velocity of B denotes the absolute velocity of the cannonball in meters per second. Then what is, yes, value of theta. Value of, yeah, value of theta is given to be 48 degrees in the question. Okay. Yeah, yeah. Because if you, while solving, if you find something is missing, you check the question again. It would have to be given, unless, of course, the answers are in symbols, it will be given. Or there will be some geometric relation at connecting it. Okay, then. Yeah, yeah. So, the absolute velocity, it is the same drill. We are just connecting it with the RFR now. So, velocity of B is nothing but what is the symbol it is hinged at? Let us call this O. Okay, let us call this B. So it is velocity of O plus omega cross R of B with respect to O plus VREL. Okay, so we know this doesn't move. This is 0. This is 0. Omega we know. R of B with respect to O we want to know. VREL we have been given. VREL. VREL magnitude we have been given. Naturally, this will be along, both are measured along the slot. So its unit vector is that way only. So we can write that unit vector in our Cartesian components, x and y. It is a simple issue. So our VB, let me solve it in a new page. Okay, so VB is VO became 0. This was 0.577 K cap crossed with R of B with respect to O. Oh, okay. R of B with respect to O is what we were seeing. This we wrote. This follows. R of B with respect to O is, this is 6. This is 6 and this is theta is 48 degrees. So it is nothing but 6 cos 48 I plus 6 sin 48 J plus VREL. VREL can be, see, VREL vector can be thought of as VREL magnitude into its unit vector. Unit vector is along the this thing only, along the barrel only. Magnitude is given to be 25. So it is nothing but 25 into cos 48 I plus sin 48 j. VREL, yeah, so everything is accounted for. So VB we can calculate from here. It will be minus 0.577 into 6 sin 48 plus 25 cos 48. This will be the I component plus 0.577 into 6 cos 48 plus 25 sin 48. This will be the J component. So what does this come out to be? 14.15 I plus 20.90 J. I hope it adds up. Okay, so this is 14.15. This is 20.90. Okay, Then what else is asked? Magnitude of Coriolis acceleration acting at that instant. So Coriolis acceleration we saw it is nothing but 2 omega cross VREL. Magnitude is asked, so we can simply multiply them. 2 into 0.577 is what we got into VREL magnitude is given to be 25. So 50 into 0.577. So it is 28.85 meters per second squared. If A denotes the absolute acceleration, so of course this is the last piece of the puzzle that also has been asked. So acceleration of B is nothing but acceleration of O omega cross R B with respect to O plus alpha cross R B with respect to O plus 2 omega cross Brel, which is the Coriolis component, plus Arel, which is the relative acceleration, which we see from there. So you see, when we are given relative quantities, uh, because from the construction of that cannon, the construction will have a spring, compression spring, which will release its energy, and the ball will be shot out. So we only know its velocity relative to the barrel, and the barrel itself is moving. So ultimately, we have to calculate the absolute quantities. This is why rotating frame of reference analysis is important, because generally we only get relative quantities. If you have a plate and you put a motor on top of it, you know what is the motor's RPM, but that is relative to the plate. So these relative quantities uh, have to be accounted for, and the absolute values have to be determined. This is why we are doing this. Okay, that is barrel is vertical at that point. So theta is 90 degree, you're saying. All right. O, if O point O has any acceleration. O is fixed, no? Okay. Yes, if it is in contact, it will be delivered. Yes. Yeah, that means free to move means you are implying that there is loss of contact, right? Ah, yes. So if there is loss of contact, nothing is delivered. If the contact is maintained, suppose if you look at it while rotating at an instant, you look at it. It just you took a photograph exactly at when it was perpendicular. This doesn't tell you any information whether it has lost contact or whether it was to like that to start with. So in such a case, the question or the problem would have to be qualified a little more as to what is the instant we are looking at. Is it just an instantaneous phenomena we are looking at, or is it by construction like that? If it is by construction, there is loss of contact, then you don't have to deliver anything over it. Okay, yeah. Okay, so I think I wrote it somewhere. Yeah, this big expression. So let us just calculate this. Zero 0.577 only we took, na? Yeah. Cross 577 K cross. This was 6 cos 48 I plus 6 sine 48j plus 0.6 K cross this same thing. Okay. Plus 2 omega K cross VREL. VREL we just wrote it as 25 into cos 48I plus sine 48j plus ARL. A I think it was given to be 5. So it will just be 5 into cos 48I plus sine 48j. So I think I'd rather leave you with this solution. It is a trivial matter to do the cross products and get the answer. That is not much interesting. The problem, the part which is interesting is how do we formulate it and how do we write the relevant quantities. So when I post this, I'll do the solution and post, but I would rather skip that now. So if there are any questions in what we have seen, uh, They are welcome. I will try to answer them. Yes, what is it? Yes, yeah, 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 yeah. We have the velocity of 2 points. They are concentric circles. So I consider this is my point. This is the velocity now. At some other point, at some other instant of time, this would have moved like that. Relatively, it would have moved like that, and this will be the velocity. So if you see, if you copy this, I translate it to this point and then I rotate it. I translate it to that point and then I rotate it to get. Is it having two components of motion? One is translation to that point and rotation. So both these constitute general plane motion. Yeah, is it clear? Okay, I will just no, circular motion is relative to one point. See, in the lecture, what would have been discussed is there is an object like this. Okay, this this actually is having general plane motion, which can be thought of as a translation, and then about one point rotation. So that is decomposition of general plane motion into translation and rotation. The question which was asked in the tutorial, in the assignment, it is two concentric circles. Okay, these are two concentric circles, and I suppose there was a disk here, something like that, right? So let me color this portion. Let me color it red. Okay, and let me color this green. So now you just think about this, that if at this point when it comes, okay, at this point when it comes, where will be red color and where will be green color? No, no, for the other students also who had asked. So, see how that can be achieved. This thing. See, now if I take the same thing, I just draw it like that, and then I color it green, and then perhaps I color it red. Okay. So what this can be thought of is this translated to that point and then flipped by 180 degrees, rotated by 180 degrees. So in our lecture, what has been shown is the total motion can be decomposed as translation and rotation of 180 degrees. So general plane motion is decomposed into translation and rotation. But you see that it is moving in this circle. So it is actually having, although it is a circular path, any curve, it is having a translation, then it gets flipped. So our red face will be here, our green face will be here. So it is a combination of rotation and translation. That is why it is general plane motion. Is it clear? Okay, good. So there were some enchanting questions. So other than this is all I have to say. If there are any further questions, I can take it now, or else we'll call it a day. Yes. Yeah, yeah, please go ahead. No problem. Yeah, okay. No, no. See, no need to confuse both. What he meant, what the professor meant is, if you have this and then you apply a force here, and if your resultant has reached the peak, it has already, it cannot go beyond the physical boundary, then you are reaching the limiting condition. This question is, this is point A, this is, I don't know what it was called, let us call it point B, and we have a force applied here. Okay, a weight of the ladder is acting. Both the surfaces have friction. That's what is said. So if you are to tip it about point O, there has to be loss of contact at point A. You agree? Okay. So now at the, yeah, at the instant when there is, let us assume that there is loss of contact there. So the entire weight has to be borne by this point for it to be in static equilibrium. So what is the maximum Frictional force that can mobilize here, it is mu n, mu w. Yes, mu n, n is w. So mu n. Now, so by equilibrium, this is also mu w. So this is so far so good. Now, moment equilibrium, if you see about this point, mu w into this for distance is the overturning moment. W into this distance is the restoring moment. Can it ever happen that mu w can be more than wd? Is the essence of the question. So this will never happen. If you pull it with wd, you cannot overturn it. If you pull it beyond that, it will never lose contact because friction is exceeded, so it will slide. So a ladder like this will become like this, will become like this. It will never lose contact with the wall when you pull, because the the force required to overturn it can never be achieved. Friction can never offer that. Is it clear? Okay. Two different things. Two different things. We analyze it independently. It is not that if we are considering it to be two different things, body can necessarily undergo both of them. It depends on the constraints of the problem. So unless, of course, it is mentioned, you take it that we are dealing only with mu n for simplicity as of now. If it were to be like that, if mu were, then we will have to qualify this area. What kind of what kind of contact is happening over there? What is the surface like? And all those things will come into picture if we were to do a detailed study of that. So the idea is, first, in this course, we will look at the structure as a whole, try to get some forces whichever is possible. Then we dismantle the structure and then start analyzing it for stresses, strains, and all that in the next level course. Then in the third level course, there will be stress concentrations, because second level course also we will be making some assumptions. So ultimately, where this leads to is it cannot be dealt with by any course. You have to go for numerical analysis and experiments. That is what we are building to. That is what engineering is about. So any other questions? Okay, good that today it was quite participative. I encourage you to ask as many questions as possible. I'll try to answer them. So, okay. So other than that, if there are no more questions, I'll call it a day. I thank you for attending the session. Thank you. Thank you.